Welcome back to ECE 441A 541A. In this video I want to simply walk through some block diagram algebra, and we will start with this classical block diagram configuration where we have a system in the forward path and we have a feedback path that actually contains some dynamics in the form of a transfer function capital H of S. And we want to now find what is the closed loop transfer function between the reference input R and the output Y. And it may not be necessary in this case, but in general I like to simply start these kinds of problems by labeling the output of my summing junctions. Here we only have the one summing junction. Let's just go ahead and call it a lowercase e, just so that we know that we really need to get rid of that in our expression for R and Y and this this configuration. We can now write E, and this is a Laplace transform of a signal, is equal to R minus H of S Y. And I will probably go ahead and drop the arguments. R actually is R of S, Y is also Y of S. And now we can say that Y, in fact, is G times E. If we now simply replace this E in the GE expression, we find that we have Y is equal to G times E, which is R minus H Y, which is now GR minus GH Y. Let's combine the Y terms on the left, and we have 1, and now I'm assuming single input, single output, so I just have a 1 factoring out from the Y, plus G times H Y is equal to GR. And now I can divide, since it's single input, single output, I can divide through both sides by 1 plus GH, and let's divide both sides through by R, and that will give us then our transfer function T of S is Y of S over R of S equaling G over 1 plus GH. And remember that G and H in general are functions of S, or are transfer functions. This now gives us a ratio of ratios in terms of transfer functions. So this is now our transfer function associated with our classical block diagram of G and H connected in this negative unity output feedback configuration. Negative output configuration. If H of S was 1, then it would be a negative unity output feedback. In this configuration, our closed loop transfer function is G over 1 plus GH. Let's look at a couple more. Here, if we look at this particular block diagram, now our H of S is 1, it's unity, and our G of S has now become D of Z G sub P, D of S G sub P of S. So that now when we're writing our transfer function T of S for this block diagram to be the ratio of the output's Laplace transform to the input's Laplace transform, again, if we say that, well, that's just G over 1 plus GH from our classical configuration, G now is D G sub P, and H is 1. And now we see that the transfer function between the reference input R and the output Y in this negative unity configuration with maybe a controller transfer function and a system in the forward path, in the cascade path, Now we're combining those by simply multiplying those, and we get dg sub p over 1 plus dg sub p for the transfer function there. Something similar in this block diagram. This, you could say, is a block diagram with a pre-filter, where here is our pre-filter, f of s. The right-hand side is really just our previous transfer function, and with this pre-filter, that's now in cascade with that other transfer function, or this transfer function, t of s. The ratio of y of s to r of s is now the dg sub p over 1 plus dg sub p in cascade with the f, or this is now dg sub p f over 1 plus dg sub p. Again, that's pretty quick, or we can find that pretty quickly by already knowing this classical configuration, giving us dg sub p over 1 plus dg sub p, and realizing that that's now in cascade or in a series combination with this pre-filter f of s. Suppose now that we look at another slightly more complicated block diagram. Here we actually have two summing junctions, and to keep things straight, a lot of times what I like to do is go ahead and label each of those outputs of the summing junctions. So let me call this particular signal E1 and this signal E sub 2. You could call them whatever you want, you just need to keep track of them. And now we can see that E1 is equal to these two signals. The top signal coming from the top is D1R, and the signal coming in from the left is a plus D E sub 2. And if I'm not indicating otherwise, you can assume that if I'm unlabeling the signals coming in to a summing junction, those will come in with a positive sign. We now have E1 written in terms of R and E2. Eventually we want everything written in terms of the input signals transform R and the output signals transform Y. Let's now rewrite or find an expression for E sub 2, and that's simply R minus Y. We can use this E2 to get rid of the E2 in our first equation, and we have D1R plus D times R minus Y. And we know that Y is equal to, from this block diagram, the way that we've labeled it, Y is G sub P E1. Let's now plug in the E1 that we most recently found an expression for, and we have G sub P times D1R plus D times R minus Y. Let's distribute all of those terms, and we now have G sub P D1R plus G sub P dr minus G sub P dy. Collecting terms that have common y's and r's on the left we'll pull out, and we're again assuming single input, single output. We have 1 plus G sub P d, all multiplying y on the left, and on the right let's factor out the G sub P. We have a d1 plus d times r, and now we can solve for the transfer function t of s, being y of s the output over the input's Laplace transform, and that's now G sub P d1 plus d over 1 plus G sub P d. And now you can compare this transfer function with some of the previous transfer functions. If you look at this relative to the classical configuration, you can see that if we set d1 equal to 0 here, we get our original sort of negative unity feedback with a controller and a system combination, and that falls out of this transfer function. If we set d1 equal to 0, we end up with g sub pd over 1 plus g sub pd, which is what we would like to see, that we do get consistency. One more, just for fun, that involves a couple of summing junctions. And again, these are 2 degree of freedom controllers. We have a d and a d sub 2, so there's 2 different places where we can introduce some design activity. Let's now suppose in this configuration that we label this signal e sub 1 and this signal e sub 2. E sub 1 is now coming in from the left, d e sub 2, and coming from the bottom, minus d sub 2 y. E sub 2 is r minus y, and again y is simply g sub p e1, and we're trying to find one equation that only contains y's, r's, and these transfer functions. Let's now plug this e sub 2 into the expression for e1, and we have d times r minus y minus d sub 2y, and let's use that e1 here, and now we have g sub p times d r minus y minus d sub 2y. Distributing those terms, we have g sub p dr minus g sub p dy minus g sub p d sub 2y, collecting like terms, and we have 1 plus g sub p, the product of d plus d sub 2 times y is equal to g sub p d times r, and our transfer function in this block diagram, which is the ratio of the output to the input's Laplace transform, is now g sub p d over 1 plus g sub p times d plus d sub 2. And again, we get back what we would expect to get back if in this block diagram we set d sub 2 equal to 0. Then we should end up with our g sub pd over 1 plus g sub pd, and in fact we do. But you can also see that we now have more flexibility in designing the numerator and denominator transfer function for this configuration. Now we have additional freedom in the denominator of our transfer function t of s for this configuration. In this configuration, we now have some additional flexibility in the numerator of our closed loop transfer function in the form of the transfer function d sub 1. So that gives you a feel for how to find transfer functions from some of these classical interconnected block diagrams, and hopefully you can see that labeling the outputs of the summing junctions can be beneficial to find one equation involving only the input's Laplace transform r and the output's Laplace transform y.